So we are back to read a paper. Probably, I guess it's safe to say the last paper read for 2025.
Yeah,
We started 2025, right? It hasn't been a year. It
it,
has.
it, yeah. We started like in the summer, I think, right?
Oh, really?
Yeah,
Okay.
yeah. It's been on and off.
Yeah, I think we read like six, seven papers, and
Uh-huh.
okay. Uh, okay. Let's read this one. It's Hotness 2025. It's short, right? 7 pages.
Yeah, like six and a half.
Okay. 6, 7. Okay, rethinking the cost of distributed caches for data center services. And it's an all-star cast, right?
Hmm.
Like Ion Stoica, Scott Shankar, Matei Zaharia, Atul Adya, and oh yeah, UC Berkeley Databricks, ICSI. What is ICSI? Okay, Scott Shankar is there. Must be something networking. Okay, this paper systematically studies the cost impact of distributed in-memory caches on data center services. It's a great paper, right? I mean, everything is about economics at the end of the day, and this is data center economics and you know, caches, distributed caches. They do a lot of heavy lifting, and this sounds like a promising paper. While memory use for these caches is often perceived to be expensive, hmm,
Hmm.
we find actually, I don't like this color. Hold on. Um, we find that the resulting CPU savings from these in-memory caches far outweigh the cost of added memory. Makes sense, but it's very interesting. In fact, across a variety of, hold on, just across a variety of both synthetic and production workloads, we find that adding distributed in-memory caches can lower total operating costs by 3 to 4x. Wow, holy cow. Even without considering their latency benefits. Wow. Hmm. Really? We are talking about money saving.
Well, yeah.
Oh, wow. So this is basically not waiting on the CPU. We could use that for more operations, and that's monetary saving.
Well,
Wow.
it is money savings, right? It's all about money. It's all about like, yeah, you're saving CPU so you can do something else, right?
Hmm.
Or like you can, provision less,
Yep.
for example, to support your
Yeah.
data
Yeah.
storage, right?
Yeah.
And rely more on these caches,
Yep.
right?
Yeah.
One thing that comes to mind, of course, like to me, right, is the metastable failure risks,
Oh, yeah. Okay.
right? And like the DynamoDB, like in 20, what is it, 2022, like DynamoDB paper, right? They have a very lovely section where they say, well, caches failed and, we failed, right? And, we don't know how to deal with it. So we just make sure that our underlying storage, can handle like 100% of the workload, right?
Yeah.
So
Yeah.
the opposite of money savings for the reliability
Oh.
purposes.
That's a good point, right? So money savings, but we should revisit, think about the metastability effects, right? I remember the DynamoDB paper basically said that, yeah, we get from the cache, but we still exercise it. The
Mhm.
the 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 servers so that they would be ready to handle the load if the caches fail and we have to fall back to them. That was interesting.
Yeah, yeah. So like in that sense again, like the operating costs or savings is not
Mm,
surprising to me, right? Like
mm,
what would be surprising is if you can get those
mm,
savings without hidden penalty somewhere, right? Hidden cost
mm.
somewhere or like a deferred cost.
Yep, yep. Okay, let's keep on reading. But
Hmm.
I like the topic a lot. I mean, this is a great topic to look at. I mean, people working on cloud services learn about these things, but it's good to see this analyzed, formulated, and shared. Okay. These cost savings can vary significantly across various architectures, such as storage layer caches, mhm, remote look-aside caches, and in-memory linked caches. I guess we are going to see these architectures in the paper. We additionally evaluate cost for two emerging scenarios: caching rich application objects and strongly consistent cache. What is rich application objects and strong?
Emergent scenario.
You will see, okay. For the former, we find that caching application objects provides outsized benefits compared to their denormalized key value style variants. What the? Up to 8 times compared to reading from storage. Denormalized key value style variants. Okay, we will see. For the latter, we observe that even a minimal version check for consistency can eliminate most of the cost benefits, calling for new designs for cost-effective, consistent cache.
So I
Oh,
would say, rich application object is, caching the actual like, whatever structures or objects that the app needs, as opposed to like caching maybe at the underlying level, like key or
mm,
where you still need to like uh, compose those objects from the cache data.
oh, you mean like this is already hydrated and
Yeah, yeah.
something like that. Okay, I see. Okay. Okay, let's read. Alex, your turn. Introduction.
Okay, introduction. So, in-memory caches are widely used to achieve low latency in data center services that tolerate eventual consistency. Several links, several citations.
Hmm.
Popular implementations include remote caches like Memcached and Redis, which
Yep.
often serve as look-aside caches.
Hmm.
Additionally, many storage systems natively support automatic caching of popular tables and rows for fast lookups. More recently, um, in
Hmm.
linked, more recently, linked in-memory key value caches have been proposed to further reduce latency by avoiding costly network hubs, data deserialization, and overreads.
Okay, let's look at two just to see what this is about.
It's yeah,
Okay, Atul
2019.
Adia.
Mhm.
Okay.
Hmm.
Uh, okay. While in-memory caches are valuable for bringing down service latency and are widely deployed, we find a lack of research on their monetary cost. Yes. While it is well known that caches improve performance, the cost impact of these in-memory caches beyond performance benefits for data center services is not well understood. From discussing with practitioners in both database and systems community, many believe that cost of memory in the cloud makes achieving low latency appear to be expensive. Many
Uh,
believe to be even the reverse. Okay.
have you looked at the cost of memory in the past
Recently,
2 months?
I know it's going crazy, right?
So the timing of this paper may not have been.
Yeah, yeah. Uh, so this didn't age well. Hmm.
It's like I don't know, like the retail cost of DRAM is I want to say 3-4 times higher than
Hmm.
it was like half a year ago.
Hmm. Yeah.
3-4 times higher, and they get the 3-4 times the
Hmm.
cost improvement. So
Yeah.
maybe it's a wash.
Uh, DRAM is approximately 32 times more expensive than storage, now even more
Yeah.
expensive.
Well, hopefully it's temporary.
And cloud operators reported that memory can constitute 50% of server cost and 37% of total cost of ownership. Okay, cool.
Mhm. This paper presents
The reason for the memory prices to go up is machine learning, right?
everything is machine learning, right?
Yeah.
The reason for everything is machine learning nowadays. Um, so yeah, this paper presents a systematic cost study of cache deployments for data center services with three new observations. First, adding this low latency in-memory caches can reduce demand for CPU by so much that it not only makes up for the added cost of the memory, but significantly reduces total operating costs of the application. Across both open-sourced production traces from Meta and traces of a large-scale data platform at Databricks, operating costs can be largely reduced by 3-4 times. Additionally, we compare the cost savings across various caching architectures and show that cost can be further reduced by another 2x using linked in-memory caches, which saves CPU in an application itself for data deserialization.
Yep.
Compared to provisioning the backend data store with more memory, deploying external in-memory caches brings surprisingly large amount of cost saving by saving CPU cores.
External in-memory caches. This is what they call this linked-in memory caches, okay? Linked-in memory cache. We'll see.
I don't know. I think that's just a sentence that summarizes the entire paragraph.
Say this again?
I think that sentence is just a sentence that summarizes the entire paragraph. External memory caches are just distributed caches in general.
Yeah.
Second, we observe that caching benefits.
No. Hold on. What did you say about distributed caching?
I'm saying that this sentence, external memory caches, is just a generalization of the paragraph. It's just a conclusion for the paragraph.
Yep. Second, we observe that caching benefits rich object workloads disproportionately. While the caching research community has focused on traditional key value scenarios, rich object workloads are also prevalent in practice and often emerge organically as application and storage schemas evolve over time. For example, in our experience at Databricks and prior large-scale deployments elsewhere, simple read paths gradually accumulate logic to join, filter, or verify various metadata. As a result, is this talking about materialized working state or something? As a result, even ostensibly simple operations, that is, for example, retrieving metadata for a user-defined table, translate to multiple expensive storage queries. Yep. That's what they call rich object workloads. In a representative case, our internal data governance platform, Unity Catalog, which offers a unified namespace for data assets, right, metadata. Catalog data. Employs an entity relationship data model. Serving a single rich object can require as many as 8 SQL queries. Our key insight is that linked-in memory caches embedded directly in the application offer outsized benefits for these workloads, 2 times greater cost savings than an denormalized key-value style variant of the same application. Rich object workloads exhibit a fundamentally different caching profile and requirements than traditional key-value scenarios. While the typical strategy today is for these applications to read directly from storage, expressing application logic in a sequence of SQL queries, given the massive cost benefits, these applications deserve dedicated architectural attention with better caches. Yeah, that's interesting.
Makes sense.
But yeah.
I mean, essentially, it says, don't cache your queries results, right? If your object is made out of multiple queries, right? Multiple instructions, cache the entire thing.
Yeah.
Like it's all about the granularity of what you cache.
Yeah, good point. And databases don't have something. Yeah, they don't have it, right?
Well, I mean, databases would have caches, right?
Yeah, but this is
you would have you will cache, a lot of things inside the database, right? I was supposed you would cache, query plans and whatnot for commonly run query types, right? You would cache maybe most frequently used pages, right? So But yeah, like, this is a different granularity of caching.
Yeah. Yeah. Okay, go ahead, Alex.
Okay. Third, we observe that emergent requirements for consistent caches can nullify most of the cost benefits of these distributed caches. In Databricks, driven by customer requirements, there is a need to scale services with low latency while preserving consistency, linear usability. Continuing with the cost study, we observed that even minimal version check in storage for reads can significantly increase cost.
Sure.
Matching the cost advantages of an eventual consistent cache while maintaining strongly consistent read is challenging. We argue that this need not be the case, and cost-efficient, strongly consistent distributed caches should be considered an important area of future work.
Yeah. I mean, weren't
Mm.
there already some work? Like, didn't Facebook do some uh, memcached for Tau? Um,
Well,
it not
Tau
gonna
is not
step.
strongly consistent,
Oh, yeah.
right?
Hmm.
So like, what would be the challenge in strong consistency? Like the number one challenge is, of course, keeping things
Yep.
synchronous, right? Like
Yep.
your cache coherency is the problem,
Hmm.
right? So, but then
Hmm.
maybe if the database is not, I'm speculating at this point on how to
I
design
mean,
something like this, right?
leases. I guess you would have leases. You
Yeah.
would have to trade off the update cost by giving it some time, so that the leases would expire at caches, and caches would not be able to renew the leases because it's expired, and instead get the new version. Interesting. Okay.
I don't know, man. Like, if the data changed on a store, right, your cache has to be invalidated. Like the
Yep.
fact that
Yep.
you go into the
Right. Right.
cache
Yeah.
needs
No.
to
I
either, again, the lease needs to either prevent the ability to write,
Yeah, exactly. That's what I was thinking. Like batching it. Hmm.
or you need to go and check with the database, pay the cost of this,
Yep.
uh, synchronization cost, essentially,
Right,
right?
right, right. So
But then you will
basically,
need to make the
leases match that synchronization cost by trading off with the
yeah,
update
but
cost.
here is the thing, right? The problem that they discuss here is not so much latency savings, right? But like money savings,
Yeah, yeah,
right? If latency is not a problem for me, or it's not much of a
yeah.
problem, right? Maybe it's okay for me to pay the cost of that synchronization if I can make it CPU cheap.
But it's saying the cost of synchronization is too much monetarily. So,
Yeah, but that may be because, when you do this cost of synchronization, like the version check and whatnot, right? It's just too expensive on the storage system. Like it needs to go through a bunch of other things that it doesn't,
yeah.
like expensive things, right?
Hmm.
IO and disk and network and blah, 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 all the internal stuff,
Hmm.
you know. Anyway,
No,
background and
no.
motivation.
I didn't get what you were arguing for.
What's the cost of, like,
Hmm.
if you're paying the cost of synchronization, right?
Hmm.
Like the network delay, um, it can be made a lot cheaper potentially, right? If you're synchronizing with something that's cheap on a database, on a storage server, on a storage system. But if that storage system needs to do a bunch of other things, like it doesn't have that version readily available to you in its own cache, for example, right? And then it needs to go
Hmm.
and run some kind of transaction locally, right? To fetch that stuff from somewhere in storage and whatnot, right? Then you start to accumulate those costs even more, right? So
Hmm.
like maybe there is a way to make that check, while still costly in terms of latency and network interactions, cheaper on a database if you know that these checks are going to be frequent.
Hmm.
Like
Yeah.
cheaper in terms of like CPU cost, not
Hmm.
not latency.
Yeah. Okay, let's read on. Background and motivation. Distributed caches are deployed to reduce latency in data center services, yet their contribution to monetary cost has been unclear. We observe that practitioners often associate adding caches with additional cost due to the added DRAM. This work begins with the simple question: do distributed caches add or save costs? If so, how much? Section 2.1.
Mhm.
But We additionally, we are in 2.1. Oh
We're
no.
in 2.0.
Okay. Take the cost study to two emerging scenarios, caching-rich application objects and strongly consistent caching across several cache architectures. So this is background and related work.
Mhm.
Background or related work? Background, right? Okay. Background and motivation. Okay.
The cost of distributed caches. Caches are widely deployed to improve performance for data center services, as storage systems are typically slower in comparison. While it is known that caches reduce back-end load, memory is expensive and constitute a significant portion of data center cost. It is unclear whether in-memory caches might cost more than the load saved at the backend. Practitioners often assume that distributed caches improve latency at an additional cost.
Mm,
That's an interesting assumption because I would never assume that. I always associated the caches with the cost reduction
mm,
method. Um, or they are unaware of the full impact distributed caches have on cost.
mm,
Moreover, since caches can be deployed in various ways, such as storage layer caches, remote cache, application link cache, it remains unclear which deployment strategy has a greater cost impact and how this influences resource usage, such as compute
mm.
and memory.
Yep.
Consequently, determining the optimal caching architecture for cost savings is a challenge.
Okay, while cost trade-offs have been studied in HPC, high-performance computing jobs, where caching working set reduces job max span, the data center services differ in two respects. Multi-tenant services run continuously, and resource billing is decoupled across CPU, memory, and storage compared to node-based allocation in HPC. Despite their prevalence, distributed caches and their cost impact on data center services have not been systematically studied and reported. Okay, I'm motivated.
I
2.2.
think the motivation continues.
Mhm,
Caching literature has been largely focused on workloads for simple key and value pairs. For instance, the meta traces have a median value size of approximately 10 bytes with approximately 70% reads. The Twitter traces have a median value size of 230 bytes
mm,
and the mixed read-write patterns.
These are very small sizes.
Yeah. These traces reflect classic key-value access patterns, individual put, get, and delete operations on small items.
Mm,
While Redis supports cache and data structures such as lists, it does not support graphs, nested structures, or any object with internal semantics. Although research prototypes have added richer semantics such as transactional consistency, production caches are still deliberately lightweight and single operation oriented.
Wait, like there's Redis, right? Oh, okay. It's talking about Redis.
Yeah.
While Redis supports caching this or an object with internal semantics, oh, it does not support graphs, nested structures. Oh, you are even going for graphs, nested structures, and objects with internal semantics. Okay, I see. Okay. However, what? You are confusing me. Although, however, production caches are still deliberately lightweight and single operation oriented. However, rich application object workloads are prevalent in practice. Okay. Okay. These objects have internal application-specific semantics. A single request to retrieve an object table metadata gets translated to multiple operations, such as retrieving permission, dependencies, constraints, and data lineage. Each piece of this information is stored in separate structured tables in the backend, accessible via SQL. After retrieval, the application logic decides to return result to client based on the values retrieved. Often these application logic cannot be easily expressed as simple computations and often involve semantics that do not fit neatly into basic data structures. These application objects can also be parameterized based on each request. For example, a dashboard call, such as tab and user relevant logs in the past T minutes, is parameterized and assembled on the fly by joining log rows, severity tags, and ownership metadata, which are difficult to express in fixed key value blobs. These complex application logic can also subject to updates by developers, be subject to updates by developers. Since traditional caches cannot express application level logic, yes, I mean, that's what caches are about. They don't express application level logic. The most common of all, and they are saying that they should be.
Mm-hmm.
The most common, but then that's like custom coding your application. That's designing your caching layer yourself.
Yeah,
Which
yeah.
is like the materialize guys do, right? The materialize company, they have these materialize views, almost like a data flow, because these are not simple things, right? Very complex.
Mm-hmm.
I mean, if you are going to do it by hand, that would be very application specific and would be changing even within the same application over time. Otherwise, yeah, I mean, there is a reason why caches are application agnostic because they become more like black box and reusable. Okay, my rant is over. With rich objects is to express application requirements in a sequence of storage layer queries that executes on every request and rely on applications to process and compose records. Unlike traditional key value scenarios where values are small, combined to blah blah blah, orders of kilobytes and even megabytes. Okay. Now we have architectures, figure one, right? So
Well, figure
2.3 is
one
like the
is
top one.
2.4. 2.3
Ah,
is need for
2.4. Okay.
consistent cache.
Okay.
To be honest, I think, like 2.1, 2.2, and 2.3, could have been like omitted because they talk about all of this stuff in the introduction, right? Like,
I know, right? This is a lot of padding for a six-page paper,
mhm.
and we have been seeing this recently a lot, right? I feel like when we are reading, we always find, well, why is this so redundant?
Well, that's actually how LLMs write, but beyond the point.
Another thing, right? So I asked, why does the paper have a different subtitle in the page header? And you told me this is the name for the previous paper by similar authors in Hotnets
Yeah.
24. Copy paste error, because this is not the title of this paper. This is their Hotness 24 paper again. This again about caches, but cache freshness. Now we are talking about the cost of caches.
So the need for consistent cache, right? While caches are traditionally used for services that tolerate eventual consistency, such as social media and applications, many emerging distributed applications require strong consistency, particularly linearizable reads that always reflect the latest write. For instance, Unity Catalog, which centralizes access control and auditing user data, requires linearizable reads for correctness, yet is also expected to offer low latencies for a real-time user experience. Okay,
Mm.
low latency. Okay. Likewise, a system in Databricks that lets customers schedule and execute SQL queries on elastic compute clusters is tuned for fast responses, but also requires strongly consistent session state, as any inconsistency can yield incorrect query behavior. These requirements are not unique to Databricks. Other large-scale companies such as Dropbox, Google, Meta have also reported similar requirements, and recent work has highlighted the need for strong consistency in latency-critical domains such as financial trading and online ad bidding. However, for these scenarios, the common approach is to read directly from storage, bypassing the cache, as caches typically cannot provide data consistency.
Yeah, cache coherence is hard, right?
Yep.
Let's check these. You Sometimes we need these references to sell consistency. Let's check them.
Well, cache coherence is hard. The answer in the past few years was, let's do the CXL, right?
Yeah. Hmm.
That can
which
also solve your like memory issues. You know, you can
yeah,
repurpose a bunch of old memory, put them in
yeah,
CXL pools.
right, right. Good point. I mean, if you can handle it in hardware, yeah. 915, and what was the other one? 9. Okay. 2002. Come on. This is not recent.
Recent requirements.
It's not recent, right? This is not recent. 915. This is also 2014. See, it's hard to find things that motivate strong consistency. And I said, let's
No,
check these things because these things
they have more,
can handle.
okay? These requirements are not unique to Databricks. Other large companies, so 44, 10, and 18. Check
See,
44.
it says recent work, recent work. 2002, 2014, and online bidding, 53. I'm going to flip out. Yeah, it's
Okay,
2013.
check 44 and 10. Uh, 44, 2023. See?
Oh, oh,
That's
I
from,
see. I thought that those were like generic. Those were generic
okay, for what is worse,
citations for the company. They are not. 44 and 10 and 18.
well,
Okay,
10
let's
is
check.
2006, Chubby Lux Service.
Oh no.
So it is pretty generic. And
Yep.
18 is 2022, cache made
Cache,
consistent.
improving cache efficiency and data freshness. No, I'll
Okay.
take it. I mean, this is like, but this is not strong consistency. This is probably Tao stuff.
Okay, caching architectures. You want to go for that?
Yeah, I'll go that. Okay. Coming back. One more. Okay. Caching architecture. Storage layer caches. Base. Oh, okay, base. Uh, Figure 1A. We define storage layer caches as those which are natively managed by the storage system, such as row or block level caches that are collocated with the storage nodes. Yeah,
Mhm.
as God intended. They serve primarily to reduce latency and improve throughput, since serving records from memory is orders of magnitude faster than disk.
Yeah.
While storage layer caches save applications from needing to manage copies of data, they can be more expensive to access since they incur upfront overheads for query processing in storage. What is this talking? Typically, only popular rows and or records are cached in storage, since the storage is unaware of application semantics. Of course, I mean black box, but do you
Yeah.
understand this sentence? They can be
Yeah, you
more.
know, to get any of the data that's cached,
Mm,
you need to parse the query and start running the query,
mm.
right? And then
Oh, I
you
see.
you either hit stuff that's, let's say you hit the blocks, pages, or rows that are in
Mm,
cache, then you're lucky. If you don't hit
mm,
them, then you know you
yep.
have to retrieve them from disk. Now,
Hmm.
that being said, this base architecture, right? Like things
Hmm.
are changing, right? With
Mm.
disaggregated
Oh
storage,
yeah, yeah,
you do have a lot more of that
yeah,
base
yeah,
caching,
yeah.
thrown in there to, kind
Mm,
of hide the effects of slightly slower, you know, disaggregated storage, right? So I think there will be some work that, like, at the very least, you do have more cache, right, in
yeah, yeah.
disaggregated architectures,
Of
right?
course, of course.
Then you start having like cache that's maybe disaggregated on itself, right? So like
Mm,
this base architecture is getting like, with the disaggregated storage, is getting way more nuanced and potentially way
yeah.
more powerful.
Right, right. Yeah, I mean, this figure one, it looks like, yeah, when I looked at figure one, I see disaggregated architecture, right? So, and you see more like page servers coming, sitting almost in between, like maybe
Well,
as in remote or maybe not linked, not linked. I
again,
think
like
maybe this.
they talk about this like application talking to storage, right? Like two
Yep.
black boxes. But what we're saying is this, like, storage right now becomes way more distributed
Yeah.
than before, right? Like than even the
Mm,
distributed storage from before,
mm,
right? And as it gets way more distributed and disaggregated, those caches that exist in storage, they become
mm,
larger and they
mhm,
become more sophisticated,
mhm, mhm, mhm.
right? So like the I think the benefit from these caches is going to be like bigger, right?
Yep.
As these disaggregated architectures improve, right?
Yep.
Especially again, like as you no longer limited by one machine or one box, right? You can have, you know,
Oh yeah.
disaggregated caches in those disaggregated architectures. Now you can cache a lot and a lot and a
Yeah.
lot more, right? You know, it's more complicated. Probably it is slower, and you still need to
Mm,
parse. Like those drawbacks still there, right? But if
mm,
you can cache more,
mm.
um, right?
Yep. Yep.
I think the benefits, you know, the things will start to shift.
Yep. Yep. Okay, Alexei. Read the remote caches.
Ah, remote caches. So that's figure 1b.
Hmm.
Oh, before I read this, for figure
Hmm.
1a, they actually don't have the cache box. I think they should have put this
Yep.
cache box, yellow box, on
Yeah.
top of the
Yeah.
storage, right?
Yeah. Good point.
Um, so figure 1b. So this is like a look-aside cache, right?
Hmm.
Remote distributed caches are used by applications to cache frequently accessed data such as popular query results or database records. Examples include Memcached and Redis, and are typically designed to offer relatively low latency read and um, and write operations. Remote caches have the advantage of being shareable by multiple applications interested in the same data, and so can make more economical use of expensive memory resources. However, being remote means the applications add a network hub on the serving path and incur CPU cost for remote access and data realization and deserialization.
Yeah. Sure.
So linked caches are
Hmm.
similar to remote caches, but instead of remote to the application server, they are linked directly into the application as library. So that's the
Yeah. Yeah.
figure
I mean,
1c.
what's going on is they are advocating more and more application-specific caching, like white box approaches compared to black box approaches. When you come closer to the application, of course, your caching will be more precise and
Well,
more
well,
custom to
it,
your workload.
not exactly, right? So for figure 1c for link caches, they still say it's a library. So it will probably
Mm,
still give them like that key value interface, right? It's just
mm,
that you don't have that network hub. Um,
mm,
so there is a big difference between B and C that I think they only briefly touch here. So can you
mm,
go to the figure really quickly?
yeah,
So in B, right, the cache is shared. They said so. I
yeah,
just read this. Right? So if you
mhm,
have multiple applications or multiple users, right, and they all
yeah,
interact with the same cache, your
mhm,
cache ends up kind of the average of all the workloads that all these users,
mm,
put in the
mm,
system, right?
mm.
Which sometimes can be good, sometimes
Yes,
can be really bad, right? Because
yeah,
the
mhm,
average workload of all the users, if these workloads are very different, is no good workload, right? No good cache
yeah,
approximation of anything. But
yeah,
the local cache or the linked cache, as they call it, right? It can
yeah,
be tailored to each individual tenant or user,
mhm,
right?
mhm,
So there is that benefit
yeah.
in addition to latency.
No, right, right, right. I get it. I think like yeah, remote could have been even better than local because less wasteful, right? So chances are that other nodes are also needed, and then you don't have to cache it in every node. You cache it.
Yeah,
Yeah.
it can be more wasteful too.
I don't know. I mean,
No,
I
no,
think you are trying to make an argument for, oh, what if so many pages and I mean, so many nodes, and this
yeah.
thing goes out of the least recently used, and by the time I need it again, it got thrown off memory. But caches are big, right? So,
Not really. I mean,
I don't know. Okay, okay. Let's keep reading. Link caches. Linked figure 1C. Linked caches are similar to remote caches, but instead of remote to the application server, they are linked directly into the application as library. To avoid replicating the cache in every application server, linked caches are typically sharded. Interesting. So that each server handles only a partition of the cache. I'm confused.
So if you have multiple workers, right?
Yeah.
Then you need to shard your workers in such that the worker doing a particular type of
I
work,
see, I see. Okay.
like a particular
So,
type of work is going to go to
right,
particular
right,
worker,
right, right,
so that
right.
you take advantage of
Right.
the
No,
cache of that
I
work.
was thinking that the cache's sharding is independent of the node sharding. Node does everything, but the caches is sharded. What you say make
But
more
no,
sense.
but
What you
that would
say
be
make more sense. Yep.
that would be for the remote caches, right? Like if you,
I know.
yeah.
Yes, yes.
But,
So I was confused. Wouldn't that be like
mm,
remote? No, this is you're right. So this is saying that the nodes are sharded and the caches are sharded with the same way.
mm.
So that each server handles only partition of the cache and load workload. Compared to remote caches, linked caches improve latency by eliminating remote data fetches and also save CPU resources by avoiding data unmarshalling overheads and the overheads problem. However, since these caches are not shared, each application incurs additional memory cost for its own linked cache if the same data is requested across multiple applications. Still, I'm confused. Like, what is
You
reference
have
3?
data.
What is reference 3? Atul Adya Slicer auto sharding for data center applications. Yeah, this is a popular paper. We should
Mhm.
read sometime. I haven't read it,
I think we
or
read
I
it at some
haven't.
point.
Did we? No.
I mean, not
Oh,
not
you
in
read.
like
Okay.
not in this, but like
Hmm.
yeah,
From a reading group or
it's a
something.
paper we definitely read, through like
Yeah,
in whatever years ago.
exactly. If I don't blog or write about it, I don't remember it. Okay. Yeah, I remember vaguely. Yeah. Okay. Again, I'm confused a bit, like because however, since these caches are not sharded, each application course edition
Not shared,
not
Murat.
shared. Yeah,
You're too tired to read.
yeah, but no, no, no.
Okay, you have data, right?
Yeah,
The same data can be accessed by multiple applications that do different things. Each application can be sharded so that you can have different workers of each application only have to deal with part of the data,
yeah. I
right?
mean,
So if you have some data some access similarity between applications, you're double caching something.
right, but it's not. Yeah, is this assuming that the sharding is yeah,
Sharding
sharding?
is application specific, but more than one application can exist for the same data.
Hmm. Figure 1C. Linked caches are similar to remote caches, but instead of remote to the application, they are linked directly. So to avoid replicating the cache in every application server, linked caches are typically sharded so that each server handles only a partition of the cache. I don't know, I'm still confused by this.
Okay, all right. Um, Look, can you see my whiteboard?
Yep.
Maybe you should unshare so that my whiteboard is
Sure.
visible for the.
Okay. Oh, I'm touching the tablet instead of the mouse. Hold on. Um, okay, stop share. Go ahead.
So you have data that sits somewhere in storage,
Mm-hmm.
right? And then you have an application that needs this data,
Mm-hmm.
app one. And this application will have a worker,
Mm-hmm.
worker one, worker two, cache
Yeah.
one, cache two. That's one application,
Mm-hmm.
right? And this is where these linked caches are.
Okay.
And then we have application 2, worker 2 1, worker 2 2, cache 2 1, cache 2 2, right? It's different application. Now, if these applications use the same data, let's say like the same data is equally hot for both applications, then they may cache the same thing twice.
Sure.
Right?
Sure, I get it. But again, so look at app1. Let's just consider app1.
Yeah.
And worker 1. Is this so cleanly sharded that worker 1 doesn't need any access to any data that's in worker 2? What if it needs it? It's a distributed transaction, right?
Yeah.
Okay.
Then I don't know. Yeah. Then you may
basically
also need to cross a cache in the same one.
Okay, thanks. This is basically about across applications. Of course, you lose that sharedness benefits. Okay, link cache with version check. Aleksey, your turn.
Okay, so that's figure 1D. For emerging applications that require consistent reads, the typical approach is for users to read directly from storage. We describe and compare a simple baseline for maintaining data consistency, checking the data version upon each read. When a read request is issued, the application server concurrently issues a version check to the storage system or a separate service and waits for its reply before returning the requested data. The version check contains only the key, therefore more lightweight than retrieving the full value. After the read verifies the match in data version, the cache read can return the cache data to the client.
Data, yeah, we looked at 44, right? What was it?
That was like the Dropbox. Something.
Okay. Yeah. Okay. Okay.
So section 3, hypothesis. This section outlines 4 hypotheses for how caches affect the overall cost of data center service.
For this, you were right. Basically, they go to the storage and they ask for the versions. They still check.
Yeah, but like in most systems, probably like that version check would not be any different in terms of what they do at the storage than the data check. Because the only difference that you may not transmit some bytes. Right? So like in terms of the CPU cycles you used on the storage, and maybe even IOPS actually, it may be the same.
Okay. Right. So let's check. Hypothesis, theoretical model, what else is remaining? Evaluation, more evaluation. How did we jump from, related work. Okay, yeah.
So they have 4 hypotheses. Do you want to like skim through that or?
Let's see. Oh, okay.
So cache safe compute offsets in DRAM costs. Since workloads are often skewed, adding extra memory can reduce CPU usage by minimizing communication between application servers, storage, and remote cache. CPU savings can be impactful because deserialization, which are computationally expensive, consume a substantial portion of CPU cycles in production cluster. We hypothesize that reducing communication overhead can lower compute costs to potentially offset the expense of adding DRAM. To contextualize these costs, on GCP, one vCPU core costs approximately $17 per month, while GB of memory costs about $2 per month. Storage required for persistence, regardless, costs $2 per 100 gigabytes per month. While we initially expect that compute savings would merely offset the cost of DRAM, we were surprised to find that compute savings were substantial enough to drive significant overall cost reduction, 5.3, for data center services.
More distributed in-memory caches, less storage layer caches. We observed that there has not yet been a cost study comparing different caching architectures, section 2.4. From discussions with industry practitioners, a common practice is to provision more memory storage layer cache in the backend to improve performance. In Databricks, by default, backend storage is provisioned with tens of gigabytes of memory per instance for shared layers cache. We hypothesize that by provisioning more distributed caches external to storage, we can reduce the memory allocation for storage layer caches. This approach can allow for a more efficient memory allocation while potentially maintaining the same or even smaller total memory footprint to achieve target performance. Interesting. I mean,
Yeah.
they have been advocating for getting it closer to the
Mhm.
application. Yeah, but this is still assuming that the application and storage, they are controlled by the same entity. Uh, uh,
Now, I
and
think this is
and they
generic
comment.
enough.
This is, yeah,
This
this
doesn't
is
talk
still.
about the reach object. This still assumes the key value abstraction, right?
Yeah, but this is still saying customizing the data center for given applications. Assuming you have that luxury, unlike using public cloud. And because you still need to figure out, okay, I deployed a lot more in application level or these distributed caches. So you still need the analysis to see how much this would reduce the
Mhm.
cache need for storage. Not straightforward, no?
Yeah, yeah. I mean, again, like it makes sense, right? Like I was saying that these
True.
aggregate architectures, push for more in storage cache, and they say, well, maybe we should not, right?
Mm,
Maybe they say, well, maybe we should push for more in application caches or close to application caches,
mm,
right? And I think combining with the next step, cache and reach objects, right? Maybe that will be uh what drives the disaggregated storage, right? Like maybe you will need to have some kind of ways to essentially offer the cache that's easier to integrate into your application at the like reach level.
mm,
Maybe the next big thing in databases will not be database, but will be the cache and sidecars that you provide.
mm, mhm. Okay, Alex, your turn.
Cache and reach objects reduce query processing and storage. For each object workloads, applications often have to execute multiple read queries, such as SQL statements that retrieve rows from multiple tables to storage. Even if the query data, such as rows, is already cached in storage. The overhead of such query amplification might lead to significant compute cost in query processing in the backend. We
Mhm,
hypothesize that caching external to storage can alleviate this query processing, and that caches are best collocated with the application so that applications can directly operate the cached data in memory.
mm. Version check increases storage overhead. To enable consistent cache, we originally expect version checks to be simple and incur minor cost in backend, which contains only the key queried. However, we find that might not hold true for modern distributed storage systems, section 5.5, where even a version check upon a read can incur query processing and RPC communication overhead, largely removing the cost benefit of caching. Yeah, yeah, interesting. Not good news. Um, yeah.
So they have theoretical model, but then they go to evaluation and say that we validate the hypothesis and theoretical model in this evaluation. And the theoretical model is only 2 paragraphs.
Okay. Let's read.
So we develop a simple theoretical model. We focus on linked caches, but the approach can extend to remote caches. Let the
Mhm,
cache size in the app server be as A and the cache size in the storage system be as D. A miss in the linked cache or the storage layer cache incurs a cost CA and CD per request. To estimate CA and CD, we empirically measure the CPU cores used and divide that by the request rate. Let NR be the number of replicas and MRX be the miss ratio with a cache size X. And then they give a formula for total cost. T is QPS, I guess queries per second, times MR of SA. So that's the server, right?
Yeah, miss ratio
The miss ratio
of the
server cache.
server A times CA, the cache, the cost of missing, MRSA plus SD times CD, where this going to the cost of missing. Oh, in the storage, the system. Okay, CM.
What is CM?
Hold on. Yeah, what is CM? Storage layer cache incurs. CD is storage layer cache.
There is
Okay, CM times SA plus NR plus SD.
but there is no CM.
I think CM is when you don't miss, right?
Okay.
And this formula is not balanced. There is an extra parenthesis after CD. That sucks.
Yeah.
CM. What is CM? C memory, cost of memory.
No, so CA and CD is a miss in the link cache or storage layer cache incurs a cost. So CA and CD is the cost of miss, right? For two corresponding caches.
What is SA times NR? NR be the number of replicas plus SD.
So again, like this is SA is the cache size. So that's total cache size plus SD, the total cache size in the storage system, right? Then it's multiplied by something CM.
I think CM is like cost of memory.
I mean, it has like C is the cost of miss ratios here, so it has to be cost of something being missed. Or maybe it's a cost of not missing because it's all like it sums all the caches you have.
Yes, I think so. Okay, takeaways. We omit derivations for space constraints and we also omit what is CM.
And a parenthesis.
And the parenthesis. We find that adding a unit of cache at the application leads to larger cost reduction compared to adding a unit of cache at the storage system. Or
actually, they don't miss a parenthesis. But...
what is the CD? Oh, right. Yeah, QPS times. Oh, I see. Yep, they don't miss a parenthesis. I was parsing it different. The QPS queries per second times the cost of miss at the server and the cost of CD.
I mean, logically, it has to be cost of miss at the server, cost of miss of everything the cost of miss at the storage plus the cost of not missing it, right? The cheap part. So I think CM may be the cost of not missing it.
Right, no, I think this is the fixed cost of the memory. Could be.
Maybe.
This is the cost of the CPU, and this is the monetary cost of the memory. Because you are multiplying the memories at each node plus the memory at the storage, right? So this is the monetary cost of the caches.
Oh yeah. So yeah, the first part is
and
about
this is the CPU cost when you when you miss.
Yes,
How much CPU you waste.
the
And this is
CPU
the
cost
fixed
is
cost of
QPS
the cache.
dependent. Okay, yeah, probably, yeah.
Yeah. A unit of cache at the storage system, or what is this? DT divided by DSA greater than DT divided by DST. This effect is more pronounced with higher workload skew, figure 2A. This means we should provision more link cache or less storage level layer cache. Wow. How? I don't get the derivation.
Well, you don't get it because
Yeah,
we omit the
yeah, yeah.
derivation.
Yeah, the optimal cache allocation is to use as much link cache as possible up to where the marginal benefit of adding cache equals the marginal cost of unit of memory when dt divided by DSA is surprisingly, even when memory becomes expensive up to 40 times than the current cost or caches have more replication, adding caches still saves cost. Okay, that's interesting. Figure 2, Ziphian alpha, number of replicas NR, cost of saving X, cost of saving X. Okay, let's move on. I get a vague idea. Evaluation.
We validate our hypothesis
I
and
mean,
theoretical
like,
model.
Alexa, wouldn't
Yeah.
it be better if they used pages wasted for section 2
Yep.
and instead, you know, in section 4, the theoretical model, so we follow along and we could do similar calculations.
But again, that's not how LLMs write. The LLMs
Mhm,
write in circles.
mhm. We validate our, go ahead.
Yeah, we validate our hypothesis and theoretical models by comparing designs on synthetic and production workloads. We first show that CPU cores saved by adding distributed caches far outweigh the provisioned memory.
Mm,
Next, we highlight that caching rich application objects brings outsized cost benefit up to 8 times compared to directly. Again, they
mhm,
summarize
mhm.
on the same thing in the
Same
introduction.
thing again.
5.1 experiment. Cache. The remote cache and application are implemented as gRPC services. Each application server is provisioned with 6 gigabytes of memory for cache.
Mhm.
The database. We use TIDB as a representative distributed database with 3 TIKV pods and 3 TIDB pods.
TiDB.
How do you pronounce it?
TiDB, TiKV.
Okay. Each TiKV pod is provisioned with 15 gigabytes of memory, and these pods rely on block caches for caching popular rows. For years, I've been calling it TIKV. Uh,
Mhm, mhm,
Cost model. The total cost is based on compute with CPU cores and memory used, multiplied by their unit costs on GCP. Although cloud providers charge per VM minute, most production platforms today are provisioned according to peak CPU utilization.
mhm,
A citation would be,
mhm,
yeah. Lower steady-state CPU demand maps directly to smaller VM shapes or fewer replicas when autoscalers trigger on
mhm.
compute utilization.
I mean, this is interesting, Alexi, right? So we were thinking, are they saving the money for CPU not being wasted? But it is coming like they are doing something simpler, more coarser. So they are going with the peak CPU utilization um, base cost estimation, it looks like.
Well, again,
So,
like, yeah, if you need to provision stuff, right, capacity planning and whatnot, you will
mm,
provision for the maximum you will need, right? So
yeah,
I think what they're trying to do is they're trying to lower the peak, not the
yep,
actual
yep,
on-demand usage.
yep. It seems like that. Hmm. Okay.
Where we are. Lower steady-state CPU demand maps directly to smaller VM shapes or fewer replicas when autoscaler trigger on compute utilization, while practical constraints like VM sizes and the need for over-provisioning can slightly skew results. We believe cost and VM shapes, such as those supported by GCP, and advancements in resource disaggregation can help mitigate these issues.
Workloads, synthetic workloads. We use 100K keys with Zipf-in access patterns. Alpha is equal to 1.2. We vary the read ratio R from 50% to 99% and the value size from 1 kilobyte to 1 megabyte. Open source, I mean, they are already talking about big sizes, right? Because we have seen that 10 bytes for Twitter and this thing for Meta, and now they go directly for 2 kilobyte to
Well, the
megabyte.
very next sentence, Murat, read it.
We use traces from Meta, which have 30% writes with median value of 10 bytes. Oh,
So they have syntactic workloads where they try bigger stuff, and open
I
source
see.
traces.
Yep. The trace contains reads and writes over key value pairs. Okay. Analysis of using cat trace distribution. Figure 3. Is figure 3 synthetic workload or
I think it's their production
open
workload.
source?
That's the next paragraph.
Okay, you read it.
Production workloads. We use production traces from an internal data governance service, Unity Catalog, in Databricks. Unity Catalog models data using a hierarchical namespace. At the top is the meta store, which defines a three-level identifier, catalog.schema.table, and tracks metadata ownership and privileges. Within a meta store, catalogs group related domains, for example, by business unit, and contains schemas. Schemas then hold secureable objects such as tables, views, and functions. Privileges are granted to principals, users, groups, service principals on any level and inherit downward. The workload is read-heavy, 93%, handling approximately 40,000 complex query per second. The median value size is 23 kilobyte, with large value at the tail.
I mean, they finally defined QPS here, so that's fine. Get table is the most common operation and incurs most costs, which retrieves data governance and access control information about a particular table. Get table translates to up to 8 SQL queries directed at multiple tables in the database, such as permissions, constraints, and privileges. I mean, yeah, isn't it? Can't you pin some things to cache? Aren't there primitives that let you do that in programming, right? Because I would have want this catalog to be pinned to cache and not worry about it being, I don't know. Yeah.
Well. So again, it's the hierarchical nature of it is somewhat of a problem, right? So
Mm,
you have a table, so and for each table you have permissions and blah blah blah, and then you probably need like a higher level of hierarchy, and then you merge them. So
mhm,
I can see how it may get into like multiple queries. Maybe not using relational database would be a solution here.
mm, mhm, mhm.
Like if you're doing get table and all of your table information is in one document in the document database,
Yeah.
right?
Mhm, mhm,
And then you can cache those documents as
mhm.
opposed to rows from the table. But
Yeah.
probably they have their reasons, right?
Mhm. Okay. Figure 4. Comparison of total cost for different architecture based on varying value, size and read ratio. Figure 5, cost comparison of Unity Catalog KV and Meta. Okay. 5.3, compute saved by caches largely exceed the cost of added DRAM. We compare costs for synthetic workload in figure 4. Okay, figure 4 is synthetic workload. It's too neat. Uh, Compared to base, linked demonstrates significant cost savings, 7.3 times for large values, 1 megabyte, and 3.9 times for small values, 1 kilobyte. Since larger value incurs more deserialization, EU observes significant cost savings for remote and linked for Unity Catalog KV and Meta, figure 5 as well. So this is the real workload.
Mhm.
Remote has less cost saving than linked. Yeah, due to CPUs needed for gRPC communication between application and remote cache. Okay. Yeah, let's
So,
get
so
CXL and not worry about any of
well,
this.
yeah. So here is the thing, right? Like they build this on top of gRPC, right?
Mm,
Or even like systems like Redis and whatnot, right? They are actually hugely inefficient in terms of how they handle the network,
mhm, mhm.
right?
Yeah.
So you can build a better cache with, I don't know, kernel bypass of some
Mhm,
kind, or RDMA or DPDK or
mhm,
whatnot, right? And pay a lot like fewer CPU costs, on
mhm,
that
mhm,
potentially,
mhm.
right?
Yeah.
It's just that like no one wants to bother with,
Mm,
those things because they're complicated, difficult to
yep.
maintain and whatnot.
Yep. Yep. Okay. Next. In figure 6, you go.
Yeah, in figure 6, we present a breakdown of relative compute cost at the cache and storage layer.
Mm,
As the value size increases, writes become more expensive, and the cost at the storage layer required to serve this request constitutes a larger portion of the total cost.
mm,
What are we talking about? 6. So base, remote, linked, and linked version.
yeah.
The CPU cores,
Mm.
app server, and storage.
Right. It's looking at the cost at the server versus storage in most, because,
Hmm.
but in remote, there is also the remote cache cost,
Hmm.
which is like memcache, the other nodes maybe. And what is the pattern? The pattern is storage cost is more. Huh?
Should they put this A, B, C, and D as direct comparison to each other?
Yeah.
Because the base, like A, the scale is
Oh, the
different
scales are
than
off.
B,
Yeah,
then
yeah.
different than C, then different.
I didn't notice this. Yep.
Right?
Hmm.
It should be a direct comparison
Yep.
because they,
Yep.
they, they
Yep.
want to show which one is more
Right.
like.
Right. This should be proportional. Uh, proportional to base.
Put them on one figure.
Yeah. Or at least make proportional to base. Yeah, that wouldn't look good. Yeah, put them on. Mm. Okay. But then we see that these are lower, but still, even internally, like storage is. Oh, this is the bad one, right? This says that
Yeah.
the cost of storage make this
Hmm.
prohibitive.
Yeah. What's funny, again, right? Because it's not to scale, it looks like the cost of storage here is more than in the base, right? Because the
Yeah,
scale is different. But I think
yeah.
if you kind of squint your eyes, it becomes the same.
Mm, yeah. Okay, okay. Read it again.
Okay, in figure 6, we present breakdown of relative compute cost at each cache and the storage layer. As the
Mm,
value size increases, writes become more expensive, and the cost at the storage layer required to serve this request constitutes a larger portion of the total cost. Okay?
6A, probably. Okay.
Among the
Oh,
CPUs,
all of them. Sure.
Mhm.
Mhm.
Among the CPU cycles spent in a database, 40 to 65% of compute is spent on managing connection, query processing, and execution planning.
Yeah.
How do they get this from this figure?
They don't necessarily get it, but they are telling this us, right? So this is the cost of
Then give me the citation.
sure. Hmm.
Um, right. The rest is spent executing key value lookups and communication in replication, execution, executing queries, which accounts for 10 to 40% cycles.
Hmm.
For linked, preparing and issuing read or write requests to storage accounts for most CPU cycles at the application,
Hmm.
followed by communication between client and application, and the remaining cycles are spent on application server service in the request. So I take it these are the numbers that they got. They just don't tell their methodology or like how they arrived to these distributions.
Mhm.
And obviously it's not in the figure because that's not what the figure shows.
Okay, across DRAMs, memory contributes 6 to 22% of total cost for linked and 1 to 5% for base due to higher compute cost. Therefore, compute saved by these caches largely exceed the cost of added DRAM. Okay, when you make the y-axis same.
Mm-hmm.
Yeah, we present caching rich objects brings outsized cost savings. This is figure 7. Okay, what is figure 7?
It's right below figure
Yeah,
6
yeah.
above.
It's okay. Unit catalog object cost base link version remove linked. Okay, yep, it's clear. Okay, Alexey, read it, please.
I present two versions of Unity Catalog. The one, Unity Catalog object, figure 7. Each read request translates to multiple SQL statements to compose a rich application object. How
Yep.
Unity Catalog works in product. So figure 7 is the rich object, but
Yep.
not in a rich cache.
Yep.
And two, Unity Catalog key figure 5.
Mm-hmm.
Okay. Each read request is executed as a single key value lookup, assuming a heavily denormalized schema, which has all needed information, permissions, constraints, privileges, in a single row. Yeah, they build your document.
Mm-hmm.
Oh, my document. We know that Unity Catalog KV is significantly simplified and only reflects the data accessing logic. Actual applications often need to operate on intermediate results, such as conditional access in different sets of tables based on user permissions. Comparing 2 to 1 shows that real-world applications benefit significantly more from caching due to handling large Okay, how do I compare 2 to 1? One is figure 5, another one is figure 7.
Yeah.
And they show relative cost percentages. How do I compare them?
Mm-hmm. 7 also shows relative total cost.
Exactly. What do I compare? The two figures are uncomparable. If I start comparing number, I will say that 5, their better version is more expensive because it's closer to, everything is closer to the base.
Yeah. So they're saying reading rich objects is we
It's more
get
expensive.
more savings when reading
No, but
rich
figure
objects.
figure 7 is Murat, read. Figure 7 is the expensive version of it. At least that's what the text says. We present two versions, Unity Catalog object, figure 7. Each read request translates to multiple SQL statements. So figure 7 is
Mm-hmm.
supposed to be multiple SQL statements,
Yep.
right? That's the expensive version.
Yep.
They
Yep.
argue that they need a cheap version where you do it in one read, and that's figure 5.
Hmm.
Scroll to figure 5.
Yeah.
It's much closer to the base. The cache
Hmm.
doesn't help here as much.
Yeah.
Right? But that's
Yeah.
relative cost. Relative to what? To the base? Are bases the same? I don't think
Mm.
bases are the same
No,
here.
I think they are making my point, saying that if we had to pay each cost, having the cash makes it more worthwhile.
No,
So we
Murat.
see that these things decrease compared to the base because in the first one we still yeah.
No, look, they say that using the better version supposed to be an additional 2x saving, right? Right here, comparing 2 to 1, yeah, like in the middle of it, right? Comparing 2 to 1
Mhm.
shows the real-world applications benefit significantly more from caching due to handling large complex application objects. Specifically observe larger savings in Unity Catalog object. Okay, yeah, so that's figure 7. Compared to Unity Catalog KV, as caching application objects directly saves the application server Did they mix the figures? No. Okay, maybe I'm confused at this point. Unity catalog object is how things work in production. They say caching, that's your point. Caching gives more benefit because you do it multiple lookups.
Yeah. I mean, it's relative cost. Probably base cost is probably these don't change that much, but the base cost shoots up here. Maybe I'm
Okay,
drawing
I
these
think they're making
arrows
like
bad. Maybe this is the
this whole
it
thing doesn't
shoots up.
compute to me, Murat.
It's not the best explanation. I think what happens is these things stay the same, but in figure 7, this thing shoots up, and they are playing it loose with giving us the relative total cost, so we don't get to compare the absolute value. I think the rich objects make this go up rather than these go down. So these would be similar to these, and they have similar shape. See? But in the figure 7, basically this one shoots up, and we get figure 7. That's my new theory.
Okay. Figure 7 is supposed to be the expensive version, right?
For rich objects, it's saying that having the cache benefit us a lot. Why does it benefit us a lot? Because the base cost shoots up, whereas these costs remain the same as if it was one denormalized excess.
Okay, so
Is what
for
I'm
rich
getting.
objects that are multiple operations, you need cache.
Yeah. By storing the full materialized object in a linked cache, we eliminate query amplification, thereby reducing CPU storage in CPU storage. Okay, fine. Version checks remove the most cost benefits, and this is explaining figure 6D. We observe that maintaining data consistency nullifies most cost benefits. Yeah, comparing link plus version figure 60 with linked 6C, we observe that version checks upon read significantly increase the storage load. We had seen that in the figures. Even assuming the trivial version check, returning the rows 8-byte version column still traverses the main read path, the SQL frontend parses, and plans the query TiDB's transaction layer, validates draft leases. What? And the request, oh yeah, is sent over gRPC to TiDB, which fetches the full row and ships it back. The extra computation and communication erases most of the cache's cost savings. A key value store would sidestep some of this overhead. Version metadata can be read with a get, but doing so forfeits SQL features such as joins and transactional semantics and still incur network round trip and consensus validation, a read quorum in replicated deployments, and a RPC bypass design leveraging on NIC atomics could eliminate this overhead. Yeah, okay.
Yeah. Okay.
Okay.
Open challenges. Think they list 2 of them. Do you want to go into details on those open challenges?
Let's just read quickly.
Extending cost benefits to consistent cache. That's the open challenge 1.
Mm-hmm.
Many applications with strong consistency requirements rely on reading directly from storage. So yeah, they want consistent caches. I think that's the challenge number 1.
Yep. At this point, we understand the paper with
Yeah.
enough repetition. Yeah.
And challenge number 2, dedicated architecture for caching application objects.
Wait, did I skip 2 pages? No. Okay, 6. Okay, no. Yeah. Okay, fine. Yeah.
Yeah, 7 is very short, so you know.
7 is very short.
Yeah. So 6 is dedicated architecture for caching application objects. We demonstrated that applications with rich objects that are computationally expensive to reconstruct gain significantly more from caching than applications with smaller, simpler key values.
Oh,
Well,
so repetitive. What is figure eight? What is figure eight about? Okay,
delayed
it's
writes
figure eight.
problem.
Hmm. This was about the
It's
first
for
challenge, which
yeah, it's for
was
consistency thing, consistent
okay,
cache.
okay. And what is the late write problem? Blue represents new version, green represents old version. Cache.
You write to cache, the database is old version, cache restarts, you can.
I don't get it. Why is cache restarting? Failure?
I guess.
Okay.
I get it. It's just a cache coherency thing, right? If you wrote something
Yeah.
to cache and database is at the old version, you can lose that right.
Hmm. Yeah. Let's skip related work. Distributed caches and course. Kangaroo. I remember this name. Okay. Consider caching tiny objects on flash. This paper targets DRAM caches and shows that they too can offer significant cost savings. SSD caches may improve. Cost argues that link caches can avoid deserialization. That's the slicer work, or no? Okay, fast key value stores. However, none of the prior work. Yeah, okay. Maintaining data consistency, TTL has been widely used and studied for cache. Yeah,
TXL.
creation has been explored. Oh, that. Okay, conclusion. Same thing, probably. Okay, cool. Done. It's like
Hmm.
less than 2 hours.
Yeah. I mean, that's a short paper.
Mm, yeah, 1 hour, 40 minutes. 1 hour, yeah, 25 minutes. Good.
So, yeah, I mean, I still have the lingering question of, the cost and reliability of things.
Mhm. Oh, yeah, the metastability question still
Yeah,
remains. Right. Are these cost savings materialized or not in a real production? Because if you
because
squeeze the lemon too much, then you
it,
become more vulnerable in terms of availability.
well, see, yeah, like that's the thing, right? Like, they mentioned themselves that, you provision for peaks, you pay for peaks, right?
Mm, mm,
But what is real peak? Your
mhm,
real peak will be when the cache goes south
mhm.
and you actually need to use all the resources on the storage. You need to scale the storage and whatnot, right?
That's a
That's your real peak.
that's a very good framing, right? So your real peak would be when your caches fail and you have to do all that work. You will have to get to that peak again. Uh,
So, and if you don't have those resources, then, as young people would say, you cooked.
you're cooked. Yeah. Okay, cool. Sounds good. Good paper. I got to think about caches again, and but yeah, architecturally interesting, right? I mean, it doesn't talk about the disaggregated trend,
Mhm.
how that shapes things, but
In a sense, they argue against some
yeah,
of the things that happen in disaggregated storage, right? They say we don't need more caches in storage. We need more caches close to the
mm,
application,
mm, hmm
right? So, disaggregated storage people,
yeah,
they put
not really. I mean, disaggregated the problem the it doesn't matter where the cache is. Disaggregated says that we just need to mask the network hop.
yeah,
So
disaggregated people, they need to mask, the problems they create for themselves by
yes,
disaggregation,
yes.
right?
So they would be helped by the caches close to application as well. But
Yes,
then cache coherence becomes a problem,
yes,
right? If you need this
exactly,
consistent reads.
exactly.
Interesting. Okay, so let's say Oh, I'm trying to write too close to there and I'm not able to write anything. Okay, cool. Okay, so let's wrap it up then.
Okay.
Um, hey, thanks, Alexia. This has
Yeah.
been fun. Bye-bye.
Yeah. Take care.